All right. You're probably getting bored of me talking multiple times. I go by Reddy. I'm from Intel. I co-lead the OSF project, as you probably might have heard before. My co-presenter, Jonathan, is probably running late because he has another talk going on in parallel. We'll see if he can actually join us. Otherwise, I may have to cover his topic as well. He's from Facebook. New name is Meta. We have been collaborating quite a bit, like Ron was talking about, to enable the open system firmware solutions on Xeon. I'm going to cover the journey of when it started, what exactly we had to do to essentially move it through to the state where we essentially have OSF accepted platforms now, right? So it started like 3 years ago. We'll go through the list of things that we had to do to enable in the core boot, and how do we ensure we actually have a quality platform on top of that with a lot of testing. Brief introduction. You heard about FSP overview with in Nate and Isaac's talk. So I won't bore you with the FSP overview, but at a high level, FSP essentially provides the silicon initialization for the Xeon platforms. You can have a bootloader of your choice. In this case, in this slide, we are talking about core boot specific focus. And then we have a payload for Linuxboot to essentially boot into the operating system, do the customization, and then either boot from the network or actually boot from the local drive, right? So that's essentially the simplified flow. Now, we started this journey on the Tioga Pass, which is essentially a Skylake scalable processor, dual socket, the server, OCP server, and we did the prototype. Primarily to understand what does it take for us to actually take the client class FSP and do that on the server class, specifically for the two-socket platforms, and what exactly do we need to do in the core boot to bring up the open system firmware solution on top. This started back in January 2019, and believe it or not, our test success rate has been right around pretty low, right, 38%. Then we moved on to taking those lessons and then essentially enabling that on the Cooper Lake generation, which is the OCP server name is the Delta Lake, which got OCP accepted, a couple of last week or so. Again, this was essentially a focused effort as opposed to broad, availability for all the customers. This started back in March 20th. And we were able to actually get the firmware quality pretty high. 95% success rate is fairly high. And like Ron talked about, we have multi-party NDA discussion, the work going on to bring up the pre-launch platform, which is Sapphire Rapids next generation Xeon scalable processor. So there is a lot of work going on, and our goal is to essentially bring that platform with the core boot solution as well as the main platform solution when it gets launched, just in time kind of a thing, as opposed to doing the work after the launch. The good thing about the next generation processor, FSP package, it's really part of the full reference BIOS. So you no longer have to have any one-off statement of work type of activity with Intel. You will get it automatically. Looking back, if you look at the 2018 snapshot of what we were doing at that point to 2021, we didn't have FSP on the scale, on the Xeon platforms. We didn't have core boot features. I will briefly touch upon the core boot features very quickly. We didn't have support for the bootloader. Linuxboot was not even integrated, and we did not have any ecosystem whatsoever. Now, fast forward, we have OCP accepted platform. We are essentially working on the next generation. We have a very vibrant ecosystem, which we are really proud of. It's not just when we collaborate within the context of open community, we need to have significant number of players in the ecosystem playing the role, as opposed to just Intel doing it and Meta doing it just between two companies. It happened to be collaboration with several other companies. Jay talked about from Cispro in the morning, and we have 9 Elements, and we have Vivin, and on the ODM side, Quanta, and several other companies that have pitched in, right, to contribute to this one. So that's really truly a industry-wide collaboration as opposed to just one-off. So I will quickly go through what we have been doing all the way from 2019 days. We were brainstorming on exactly what it means from an open system firmware perspective. How do you enable it? So mostly concept level discussions back in 2019. In 2020, we talked about how do you take the FSP and then how do you bring up the Tioga Pass open compute platform for the Skylake SP. And then in 2020, we talked about how do we bring in the actual OCP platform with OCP accepted. Here is the snapshot of the OCP accepted. This is a major milestone from the accomplishment perspective on how do you take coreboot, how do you take Intel Firmware Support Package and drive the OCP accepted logo. So pretty big deal. Now, how did we get here? So Firmware Support Package has been the foundation. Now, on the Firmware Support Package, obviously, you don't get the runtime RAS. I think there were questions in the morning about, or in the afternoon, in the beginning talks about, do you really get the Firmware Support runtime RAS, SMI handler? We do not. We are actually working on that capability. There is runtime RAS functionality in coreboot that is also getting implemented. That's not publicly available. But that work is also going on in parallel. So there are two distinct ways of getting the runtime RAS. One is organically through coreboot implementation. The other one is through SMI handler, payload, taking advantage of the existing SMI handlers through FSP interface, rather. Right. So what is the open, within the context of open system firmware, we needed to make sure that we are actually using all the existing building block elements in the coreboot. Otherwise, you are going to reinvent the wheel, and then you start actually having a lot of quality issues, stability issues, and all that stuff. So we had to cherry pick the specific places where we need to instrument the server capability, like dual socket, enumerating the dual socket, number of cores. The integrated I/O is pretty complex on the Xeon platform. So we essentially had to cherry pick some areas where we had to go and extend and then take advantage of the existing building block framework across the board. That was really the theme. And then the ecosystem, the benefits, right? So Monolake, in the talk before, Jay and company were talking about OSF on Monolake platforms that's meant for circular economy, how it is helping them. Delta Lake in the OCP accepted for broader industry adoption is really the intent there. And the goal is to essentially collaborate with significant number of ecosystem partners on that one. It's one thing to say I have the coreboot code. It's totally a different thing to say it works, and it works reliably across the reboots. It works reliably across hundreds of reboots, right? That has been the focus. We spent a lot of time in testing on different platforms, different variations, and RAS capability, and all kinds of reliability tests. There are a bunch of tools out there that we used. With that, I will let Jonathan actually talk about the OSF benefits and how it helped them. Jonathan?
So yeah, thanks, Reddy. A couple of years ago, we started to launch this project. At that time, we envisioned some benefits we would reap. Now look back, right? What are the benefits we really demonstrated, we really got by doing this? One is that on the new technology development front, an end-to-end solution involves more than host firmware, right? We, as an end user, we have a vision for what feature we need, what new feature we need. But that new feature would involve so many components in the system, hardware, software, right? And the host firmware is a component inside it, and is an important component inside it. We have to own our own destiny, so we have to move fast. Another is distributed knowledge. So in the industry, the knowledge are distributed among the players, right? So how would we as a user, we would be able to get the expert together, to work together, and we would be able to understand them and work with them well. So that's our focus. So that's what OSF brings us, to enable us to do new technology development. A case study would be the CXL. CXL is a new technology, and the spec is evolving, and there's no commercial device yet. But we have to get it done. So then the reality is CXL memory stuff is not part of silicon initialization. So silicon vendor wouldn't do that. So what do? we have OSF, we can do reference implementation there. And then we get unblocked. On the server platform development, CoreBoot makes it a lot easier to debug issues. And we often use CoreBoot to find issues in other components. And that enables us to move fast. And the Linux boot enables us to do easy debugging of kernel. In the end, we need the kernel to work reliably. And when we find the kernel issue in Linux boot, we can solve it much easier than you have to put in the target OS to debug it. So this architecture, right, this OSF architecture helps with quality server development. Also, another side is that with the engineering philosophy, we have a single CoreBoot code base for all different platforms and among our partners. Right? That's really a game changer, that with the existing solution, there are so many different code bases, and they are all complex. We also have tight, very strong collaboration with partners, communities. We benefited from each other. We learn from each other when we help each other. So that really, add together, we are stronger. So benefits is we lower the development cost for us and for everybody. But the sum is big, and we get better quality. Sustaining. On the sustaining part, we benefit from Linux engineers become firmware engineers. So one set of device driver for both target OS and firmware, right? That would improve the quality and the security and time to market. And we only need one set of infra tools for OS management, for firmware management. And we have the open code base instead of closed code base. So it reduces the problem surface and enables faster turnaround. So the next step is that the OSF as an alternative firmware solution, right? It has been slower, and we are catching up, right? We are not getting leading in some areas, right? We are going to lead more and more. And on the ecosystem part, we got to production ready, but we are moving toward to industrial adoption. So the next few years, you will see more and more adoptions. Here's a call to action. So let's join together. Nobody can do it alone, right? If this is the right thing to do, then let's all join together, partner together in this transformation. So we have the OCP OS project. It's a wonderful platform that we can collaborate without all kinds of NDAs. And we also have those open source communities, CoreBoot-Linuxboot, Contest, that's a test framework, and OSF Builder allows you to build so many things together. Also benefit from it. Today you can go to buy Delta Lake server, you can build and run immediately. Within 30 minutes, you get something up and running. And you can get OCP monolith server from IT Renew, and the solution provided by Cisco. So we are happy to see that the work we are doing does not stop when we stop, right? It carries on its life, its logical lives, to impact the industry. Thank you. We now take questions?
Yeah, let's do the Q&A. Ryan, if there are any on the web, let us know as well. Yeah, go ahead.
Questions online have already been answered.
Okay, so just a question. I didn't quite understand your slide on CXL. CXL do have like a CDAT that the device is supposed to report back to the system, and the CDAT should have like the capacity of the CXL.mem and also like timing information, latency, and stuff like that.
Exactly. However, right, the current CXL spec says that CXL device needs to report to the host how big the memory, the host memory is, but it does not explain how those memory was configured. It does not know behind the CXL device how many DIMMs are there and how they were created and which DIMM corresponds to which physical space, physical memory space. So you basically get a SM BIOS table. You don't know anything about the DIMMs inside the CXL device.
So it's to allow you basically to get back from the physical address mapping of memory to get back to the fact that this is a CXL device.
Exactly. If there's a memory error, say a CXL memory error, you won't know which DIMM had a problem.
So it's to get back to the DIMM level when you have like, okay,
yeah.
I see, okay.
Yeah.
Yeah, no, because the CDAT does like have the capacity. And
That's the overall.
Yeah, bandwidth latency and all that stuff
That's
is
the
done
overall.
through the CDAT. Yeah. That's right. Yeah. Those are the standard constructs, but if you really need to go behind the scenes and say which DIMM failed, what is the capacity, number of DIMMs, you have to do a little bit of additional instrumentation in the firmware.
Yeah.
Yeah.
So
And
the spec update is in progress, and in the meantime, we're doing firmware and device firmware work as well.
And do you really want to do that inside the firmware? Don't you want to do that in ban, inside the Linux kernel or the host? Could be Windows, but.
We could do both. So all those things are on the table we're discussing. We can discuss more after.
Great question, yeah. I think we are out of time. Thanks, everyone. Thank you.
Thank you.